In this class, we will discuss about a new concept called beam column concept. So the members which undergo the effect of both axial load and moments, so they are termed as beam columns. That means the structural member, it behaves like a beam as well as a column. So normally beams they will be subjected to bending moment and columns will be subjected to compression or axial force, you can say. So here both the effects will be there. P is the axial force and M is the bending moment. So if both are acting on a structural member, so both are significant, then such members are called as beam columns. That means you can have axial compression and bending, or you can have axial tension and bending, and once again it can be uniaxial or biaxial bending. So you know about that in your RCC design. So uniaxial bending means the member is subjected to axial force and one of the moments which is significant. And biaxial bending means member is subjected to axial force as well as moments in two directions. That is biaxial bending. Now in such cases, in case of beam columns, the limit state method of design will be done in three stages. The first one is we have to consider the effects of axial load and bending separately. That means the concept of behavior of beam as well as column should be taken separately, and then we have to compare the independent effects of their respectively developed strength and stability limit states. That means whether that beam behavior is satisfied and column behavior is satisfied, then we have to compare. Then we have to recombine the effects of both beams and columns. We have to recombine as per the limit state method specifications, which is available in IS 800 2007 steel code. So these are the steps. So we have to take separately the effects of beam and column, and then we have to compare the strength and serviceability and stability criteria, and then we have to recombine the effects of both column and beam as per the specifications given in IS 800 2007. Some of the examples of beam columns are compression members in a rigid frame structure like this. So here you can say this is a rigid frame structure. Here, if you consider this column, so this column and this column I have taken here, so the loads acting on this column are P1, M1 like this, something like this, and loads acting on this column are P2 and moment is M2 like this. So these two columns, they behave as beam columns because the effect of both axial load, that is compression, and bending moment will be there here. So in such a case, if it is a braced column, means if the in the frame, if some connection, some bracing is given like this is called as bracing. If it is given like this, then the buckling of the column may be taken like this. So elastic curve of the column may be taken like this. If it is unbraced frame, then it can go like this because there will not be any bracing, so lateral stability may not be there. So that's why it may take a shape like this. This is deflected shape. So that is one of the examples for beam column. Second example, we can use cable stay bridge. So this is an example of cable stay bridge. Here this portion is called as the deck portion. This is the deck portion, that is the floor of the bridge. Then you have here pylons. These are the pylons, vertical members, which are firmly connected to the base, this foundation. So in this case, these pylons and these are the cables. In this case, what happens? You can observe the behavior of the components will be similar to beam columns. This P1 and P2, these pylons will be subjected to axial compression and bending, whereas the portions AB and CD, those portions, this is CD. AB and CD portions of the deck, they are subjected to axial compression and bending of this, of course, of this deck. Then the portion BC, this intermediate portion BC, it is subjected to axial tension and bending. So in this case, you can see the combination of compression and bending as well as tension and bending in cable stable. This is another example. The third example is connection of gay wires and cables for steel masts and towers. So in the case of steel masts and towers, they will be connected with guy wires and cables. There also tension, and in gay wires you will be having tension as well as you can have some bending effect also. So in that case, this is an example for beam column. Then this purlins supporting sheet loading placed away from the joints of top chord in a roof truss. So in a roof truss, normally purlins will be supporting the sheets, AC sheets or whatever roof sheets we are going to provide. Suppose if they are not placed properly, some difference is there, some eccentrically if they are placed, then there is a chance of having bending moment as well as forces, axial forces in that also. So these are some of the 4 practical examples for beam columns. Now to understand the behavior of beam columns, we can understand the behavior by plotting this m versus theta, that is moment rotation curve, or p versus delta, that is load deflection curve. So anyone you can plot and you can understand the behavior. So what happens, since the beam columns are subjected to both axial load and bending, so if the bending moment on a beam column approaches 0, if the bending moment is very small or if it is negligible, then it behaves like a column. Naturally it behaves like a compression member. If the axial load approaches 0, if the axial force is less and if you can neglect it, then it behaves like a beam. So both the compressive effect and flexion effect will be there depending on the value of P and M. So if P approaches 0, then only M will be there, that means bending moment, so it acts like a beam. Whereas if the moment value is very less, only if compressive force is there, then it behaves like a column or axially loaded member. So second point is they may fail by one of these criteria: flexion, that is bending; they may fail by yielding, or torsion, flexion, buckling. So these are the 3 cases of failures, modes of failure of beam columns. But the mode of failure depends on the axial load, its eccentricity and slenderness ratio, etc. So that eccentricity, if it is eccentrically loaded column, then definitely moment will be there, that P into E, it is the moment, and also it depends on the slenderness ratio. You know that slenderness ratio is nothing but L by K, where L is the effective length of the column, and K is the radius of gyration, which is root of I by A. So if this mode of failure depends on these 3 factors. Now if you observe the graph of M versus theta or P versus delta for different cases, so there are 8 cases here. You can observe here, if the graph starts from the origin, and if it is straight line like this, linear, it's a linear graph, then you can say that this one, and second one is this up to this it is, of course, up to this it is straight, then it is extended one. So then it may take a shape like this. This is graph number 1, it is a beam column. Then second one, that is it can go slightly higher and then it can take a shape like this, that is also a beam column, and the third one is also a beam column. So if the graph M versus theta or P versus delta, they are similar, of course. If they are like this, then these 3, 1, 2, 3 beam column behavior will be there. So next fourth one is a linear graph from the origin. It is extended here, so it's entirely is linear. Then that one is called as linear elastic beam. So in the case of linear elastic beam, that it only you will be having only M value, P approaches 0 then. So there will not be any axial load. Then fifth one, it is like this. So fifth one is elastic plastic beam. See the behavior. So it goes like this up to this it is linear, then it takes a curve shape like this, and then it joins this MP value. Please note that MP is the plastic moment value for that particular section. PCR is the crippling load or the buckling load. So now this joins this MP value, the highest value of plastic moment. So moment that is plastic moment it takes. So that is known as elastic plastic beam. That type of beam is called as elastic plastic beam. Next, sixth one, rigid plastic beam. Rigid plastic beam means that the entire this line itself represents the rigid plastic beam. Then elastic buckling column is seventh one. This one. That means only PCR value will be there, M value will not be there. So in all these cases, P is 0. In this case, M is 0. There is no bending moment. The beam column behaves perfectly as a column only. So only axially loaded member. So M will be 0. In such a case, the this line itself represents the seventh one. That is elastic buckling column. And the eighth one, so this one. So eighth one, it will be in between these two. So we can say that elastic interaction between bending and buckling. So that is the eighth one. So depending on the type of graph, when the material is subjected to, when the specimen is subjected to a test of load deflection or moment rotation graph, if you plot, if depending on the type of the graph, you can decide what type of behavior that beam column will have. So here P is the load, axial load, and M is the corresponding moment that is going to develop, and theta will be this angle made by the elastic curve with the initial straight line of the column, and delta is the lateral deflection, or it is also called as simply deflection. So P versus delta or M versus theta graph is drawn. Based on the type of the graph, you can decide the behavior of the beam column.